All right, I think we can get started. Okay, so hi everybody. So today I'll be giving lecture on this paper on separation logic. So why are we talking about this paper? Mainly it's because separation logic has been a great success story in verification. It's helped solve a variety of problems, including reasoning about pointers and reasoning about concurrency. Separation logic has been enormously successful in these domains for making progress in both automated theorem proving, which is what the paper focuses a little bit on, but also in interactive theorem proving of the style that we do in the labs. So actually our research group has done a bunch of work in this space as well, as far as using separation logic. But separation logic is really a foundation for a variety of proofs. This is also a little bit more theoretical, so separation logic is a little bit more complicated of a foundation than some of the other stuff that we'll see in this class. So we just want to expose you a little bit to, there is some theoretical side to formal verification and verification reasoning. And you'll see a little bit of that today. We don't expect you to understand all the details. You're not going to have to apply separation logic, but we just want to give you some appreciation for why this stuff might matter. So to that end, I'm going to start by just talking about some of the success stories. So I won't do too much on this because the paper does a pretty good job of this. So what has separation logic been good for? It was created to reason about pointer manipulating programs of various types. So there was sort of a central challenge of how do we reason about pointer aliasing, and that's something that separation logic was really good for solving. And then with pointer aliasing, addressing pointer aliasing issues, it became possible to verify a variety of data structures and reason about their correctness and memory safety. In more recent years, separation logic has been extended to concurrency. And you might have noticed that O'Hearn was almost a bit surprised by this, right? So O'Hearn was there at the original inception of separation logic, where it was intended entirely for sequential programs, for data structures, for solving this core aliasing problem. But as separation logic grew, it turns out that it was useful even for concurrency, where instead of interpreting these assertions, these things that we conjoin with separating conjunction, instead of interpreting them as representing a heap, which is what it was created for, instead we started viewing assertions as being ownership. I won't go into the details on this. We have a later lecture on separation logic for concurrency. But the core idea was this idea of fictional separation, where so we have this P star Q, and before this just meant non-aliasing. It just meant that P and Q are over disjoint portions of the heap. That was what the separating conjunction meant. Afterward, it took on a slightly funkier meaning where instead it meant something about how P and Q were compatible. Somehow P and Q could be given to multiple threads. So we had more sophisticated ideas of what this meant with concurrency. Separation logic has also been really useful for automated reasoning. So this is the kind of work that Peter O'Hearn does. He worked on it academically, and then also now he applies those ideas at Facebook, where separation logic is what makes it possible to scale these memory safety analyses that Facebook Infer does to even millions of lines of code, right? So we saw this in the static analysis paper. The Facebook one is probably largely about Infer, and Infer is based on separation logic. And the way this works is that it infers, as you maybe recall from that lecture or that paper, it infers memory safety specifications in separation logic. And it scales because it works in a per function way. So we're able to do the analyses per function and then stitch these analyses together, which means that it can work incrementally and it doesn't have to hold the whole state of the program at once, which would not be feasible with a million lines of code. I think that some of the same reasons why the automated reasoning work out are also why we're able to apply separation logic in interactive proofs. So because separation logic lets us reason about each procedure in isolation and only think about its footprint, the memory that it touches. That's what lets us stitch together these interactive proofs for large programs. Unfortunately, because the labs are small scale, you don't see so much of this scalability. So you don't see this idea of stitching together specifications into a large system. But a lot of these papers cover a large enough amount of code that it couldn't be done as one giant proof. So that's one thing to keep in mind when reading papers is how modular are they? How well did they handle each part of the program separately? Because of course, like when we write bigger and bigger programs, we need these modularity mechanisms. We need the ability to write functions and then reuse those. In the same way, we need this for proofs. Now, I should mention that this is probably the focus of the paper because this is what Peter O'Hearn does, both in academia and in industry, whereas this is what I do and what we do for our research. So there will be a little bit of a bias towards concurrency and pointer manipulation in this lecture, just because I don't know as much about the automated verification. Okay, are there any broad questions at this point before I move on? Okay, so next I'm going to start going into technical details by describing separation logic as an assertion language. And what do I mean by that? I mean, you can sort of divide separation logic into two parts. There's just the assertions that we write, the x points to y and p star q, which are used to describe the heap. And then separation logic is also about how these assertions get manipulated in proofs. So let's start with just how do we describe the heap using separation logic? So the paper talks about this picture semantics, and I'll stick to the picture semantics. I won't give a formal mathematical description of these things. When you learn about data structures, you're probably used to viewing informally little pictures that look like this, where we draw some boxes, we draw some pointers. This means that x holds the value of some pointer, and that pointer in the heap has the value y. And we draw that by, we depict that with an arrow pointing to y. P star q means there's some memory that satisfies p, and then separately from that memory is some heap that satisfies q. This is obviously like the core idea of separation logic, is this separation. This was something that was a little bit confusing in the reading question. The key thing to keep in mind is that P is not just one memory cell. P is all the memory cells that are covered in that predicate. So for example, P can have many cells, and all of the cells that P talks about are going to be distinct from the cells that Q talks about. We'll get into that more when we actually look at an example, look at the tree example. And then emp is occasionally useful, which just says that none of the heap is mapped. One slightly strange thing that you see in separation logic is these assertions describe heaplets, which are this artificial idea of talking about a subset of the heap. The heap, of course, has a bunch of other memory in it, but each assertion is only going to talk about some small part of that memory. Usually the part that the programmer interested in cares about. There's also, we occasionally will need to say things like this. This is not a separation logic assertion. What it says is that when this is formally called an entailment. What it says is that whenever P holds in a heap, Q also holds. So you can also read this as P implies Q. So now let's see an example of using this assertion language for describing a list. So I'm going to define this list of X predicate or assertion in separation logic. It's going to say that there is a heap, there is a linked list starting at X, which is going to be the root pointer. It's going to be defined recursively. If X is null, then list of X is going to say that the heap is empty, right? So that makes sense for an empty list that's just the value null. It doesn't need any heap cells to represent that empty list. Otherwise, if it's non-empty, then there's going to be some data and a next pointer, which I'm going to call z, and x will point to the combination of these two things. In text, I'm going to write this, which is sort of like an informal notation for a C struct with two fields. And then we have the rest of the list starting at z. So this gives you the recursive structure of that linked list. So let me draw the picture semantics now of this predicate. So here's an example of how list x might hold for a list that's going to happen to have two elements in it. It has a root pointer that's going to point to this struct. I'm going to depict the struct as being two cells in memory that are next to each other. That's how C would lay it out in memory. There's a next pointer, and I said there's two elements, so I'm going to have Z1 pointing to another cell in this list, and then Z2 is just going to be null, which I'm going to depict with just this black dot. Okay, so what are the predicates involved here? This whole thing is the footprint, or the cells covered by, list of x. This was a point of confusion, I think, in the reading question, where I think some people were imagining that tree of x is just the root pointer to the tree. But list of x is not just this root pointer x, it's all of the cells in the list, because those are all part of this predicate. In fact, in this particular case, list of x consists of x points to d1 and z1, and then it also has z1 points to d2, z2, and then it has finally z2 equals null. So what I've done is just, in this particular case, for this concrete list, I've just unfolded this recursive list of x. So you can see now that list of x actually has two pointers. It covers all of this memory that I've drawn here. And of course, as a subpart of list of x, we have some smaller list, the tail, which starts here and covers the remainder. This inner block is list of z1. And list of x and list of z1 are overlapping, of course, right? List of z1 is a subpart of this bigger list. This is, the paper talks about tree of x in a similar way that I've drawn list of x, where it doesn't talk about what data is in this list. It just says what memory cells list is touching. And that's because in the paper, O'Hearn is focused more on just memory safety proofs, but you can actually do more with separation logic. You can also talk about what the actual contents of the list are. And this lets you actually prove correctness of things like retrieving from the list and appending to the list. You can talk about what the actual behavior of those procedures is. Right now, if I were to use list of x to specify, let's just say I want to say what it means, I want to write a separation logic triple for appending or prepending to a list. So what this prepend function does is it's just going to allocate a new cell with A as the data, and then it's going to use the remainder of the list, the original list x, as the tail. But given this predicate, all we can say, prepend is also going to return the new head pointer to the list, right? So it's going to allocate a new cell, and that's going to become the new head of the list. The way I'm going to represent that is with this lambda. So this lambda is going to talk about the return value of prepend. This return value is going to be the root pointer for a new list starting at R. And that's all we can say. With this predicate as written, all we can say is that there is a list at R. We don't know what its contents are. We don't know how it relates to the original list. That's all we're going to say. So that's a little bit unsatisfying, because maybe we want to do more than just memory safety proofs. Maybe we actually want to prove that prepend does the right thing. So for that, what we need to do is we need to define a more sophisticated list predicate. which I'm going to call list P, which takes 2 arguments. So it's going to still take this location, this root pointer, or maybe I should really, instead of using lock, let me actually call it a pointer. And it's also going to take this L, which is a list of, I'm going to say that this is a list holding only ints just for simplicity. So here's some list of ints. Now the intuitive meaning of list P of x comma L is that there is a list, linked list at x, and it contains L as its data. And we can write this, it turns out, as well in separation logic. It's going to be similarly recursive using this list. It's going to say that if to represent an empty list, we just have emp. And probably we also need to say that x is the null pointer. So this corresponds to the base case in the other definition. The more interesting case is the case where we actually have data. In this case, a little bit similar, but instead of just having arbitrary data like we had before, so you'll see that here we had just there exists some data. Here we're actually going to say that the data is concretely this thing that's coming from the list, which we think of as the abstract state of the list, of the linked list. And then as before, we have the remainder of the list starting at Z, but with 1 less element. It's going to have the remainder of the elements in the linked list. So now we can give a more precise specification to prepend that says exactly what it does to the contents of the list, not just the memory safety. So now we can write a spec for prepend that actually promises that the new list, sorry, this should have been a list P. The new list is the old list, but with A tacked on to the front. Okay, are there any questions at this point?
I have a question.
Next we're gonna, yeah, go ahead.
You have stars at the end of your some of your statements. Is this do the stars, are you using them as was described in the paper, or do they have a
yes?
Okay.
Yeah. So this is all separating conjunction. Yeah. So there's a good point that when we say this, when we have this star here, it implies that this linked list node is completely disjoint from this list predicate. So it's what implies that we don't have cycles. It means that we can modify one element of the list without affecting the others, and we know all of this stuff. Okay, so what I'm gonna ask, well, I think now is a good time to go into breakout groups and go back to that question, the reading question. So I think there was a lot of confusion around this question, where I think a lot of people went either way, and they didn't quite understand what was going on with the question. So let me just say that the answer to the question, so recall that the question was, let's say an analogy to this list P, we define tree and it relates some root pointer, so this is also a pointer, to some abstract mathematical description, tau. So this is a mathematical tree. Now, imagine that the implementation is allowed to share nodes. So here I said these two things are going to be disjoint. Let's imagine we allow them to overlap in the tree. If it feels like it, it's allowed to make them overlap. In that case, if that's what the implementation does, the question was, suppose we have this in the precondition to some function which modifies R1. The question was, is tree of R2, comma tau2 true after this function runs or not? Now, the answer is yes, it is preserved. So now we're gonna start breakout rooms. I'm gonna set those up now. I should probably do that. And then let's just discuss this a little bit, and afterward, I'll take any questions if people are still confused about why that's the case. All right, so what did y'all think? Did you figure out what's going on here?
I guess the answer that my group came up with was basically that in the precondition, you do specify like, hey, these are separated. So then you're coming in with this assumption. So you should kind of continue with that assumption.
Yeah, that's a great explanation. What about the other breakout room?
Yeah, I think we had very similar. We were like slightly confused with like the precondition, and then yeah, I think it's also like because they're not. Yeah, the memory spaces are different, so also separated.
Yeah, so this is admittedly a slightly tricky question. So I said that the implementation is allowed to share nodes, but exactly what's going on in this case is that the fact that we have these two trees separated by a star means that at least in the precondition to this function, we're assuming that they're not sharing nodes internally. If they were to share nodes, then this precondition would be false because the same internal node can't be on both sides of the separating conjunction at the same time. So the mere fact that I set up this precondition means we have true trees rooted at R1 and R2 that have contents tau1 and tau2, and the picture here drawn is accurate. Those two things don't actually overlap. But this is also the key to separation logic, or one of the keys in separation logic, is that our reasoning becomes quite modular in this case. We know that when we modify some tree, as long as we're doing proofs in separation logic, we know that some other random tree is not getting modified. If you do want to share nodes, then the situation becomes more complicated because then updates are more dangerous. Any update could affect other trees. And so you would, if you do want to have such an implementation, separation logic can handle it, but you need more sophisticated predicates to capture the fact that they're sharing and to be able to prove, to be able to specify what updates actually do. If you made your trees read-only, then you can share indiscriminately. That's not actually a problem because then there are ways to make this sharing, to specify this sharing and make it work out. Okay, so this is one of the key ideas of separation logic, is this separation. I wanted to just flash on the screen a more sophisticated example of using separation logic for in this style of having actual data associated with a predicate, not just memory safety. So here's an extension of the tree predicate that was in the paper. There's a lot of symbols here, but one thing, let me just point out that this entire block is just a bunch of pure facts. So these are not separation logic assertions. These are just some statements that I want to make about the data in this example. So what's going on here? So what I'm specifying is that at T, rooted at this pointer T, there's a binary search tree, and it holds the set of numbers in E, which I'm going to have to be a set of integers. So recall that a binary search tree, it has some key, some number in each node of the tree, and all the numbers, and this we interpret this key as being part of the binary search tree, and then everything to the left in the left child is going to be less than key, and everything in the right child is going to be greater than key. That's how a binary search tree works. We're able to specify this data structure in separation logic, and we can combine the separating parts, the memory safety aspects, with the binary search tree parts, the invariant that a binary search tree maintains. So the way we do that is, the first part is like in the paper. So T might be none. So in this case, my representation has T pointing to nothing, as opposed to being null. Just that will be more convenient later on. So that's one case. T is just a pointer and it points to a thing that says there's no tree here. Or we have some children trees. So maybe it's best to jump down and read this, which is all the memory safety stuff, that says that T is this box. It has three things. It has a key and then two child pointers, one to L and one to R. And L and R are two subtrees. Sorry, I forgot something here, which is very confusing. This should include those subtrees have the sets EL and ER. So these are subparts of this search tree. Our overall search tree T contains the key in this root node and all the elements of the child nodes. And then we have the binary search tree invariant. So informally I've said this, which is like not a very mathematically precise statement, but it kind of captures the intuition of what's going on. Everything in the left is less than the key, and the key is less than everything in the right. So this is a pretty cool definition. This lets us capture both how this tree is laid out in memory and what it mathematically represents, this set of integers, and also an invariant that makes this representation actually work out, right? So when we implement binary search over this tree, you need this invariant to be able to implement binary search efficiently. The invariant is what tells you that you can say, so if you're searching for A and A is less than key, the invariant is what tells you you don't need to bother looking in the right subtree. And actually, just as an exercise, I was able to prove in separation logic that you can I implemented a search procedure on top of this invariant and proved it correct. And it works out pretty much as you would expect. Okay, any questions about this example? Then I'll move on to some proofs. Okay, hearing none, I will move on to talking about proofs. So the paper has a particular style of using proof outlines to present the intuition behind separation logic. And it also has these things called inference rules. These are the way that the small axioms or the frame rule are presented. So I'm going to not use either of those. Well, I'm not going to use the inference rules, but I'm going to try to illustrate what is going on in these proof outlines. And there's just one intuition that I want to get across, which is that separation logic proofs are actually quite natural, and they match your intuition for what's going on when you write imperative code. So let me do a very toy example that is not very well motivated. There's no reason why you'd write this code, but it's easy to understand because there's only 2 lines of code. So this is the example from the paper where we have these two pointers, X and Y, which have already been allocated. And what we're going to do is we're going to wire them up in such a way to make this true, right? So we're going to make X point to Y, whatever it was pointing to before, and we're going to make Y point back to X. We're going to wire them up into this little cycle. So this is going to be the post condition. The precondition is just that X has value 0 and Y also has value 0. Because of the separating conjunction, we know they're distinct. So this is good. Although I think that's not even super important here. Okay, so here's the proof outline for this example. The way I believe you should think about this is the following. When you're reasoning about one step here, by one step I mean just say going from here to here, what's going on is X, sorry, this is a store, so this X gets Y. In C, we would have written star X equals Y. Think that, right? So X is a pointer, we want to store Y into it. Okay, so the way to think about this is the proof updates the precondition in place. It replaces x points to 0, which is the precondition to the store, right? So recall that the following thing, this is a specification for stores. And so the way to read this rule is when we do a store, we find x points to v0 in the precondition, and we replace it with x points to v. That's kind of an execution first reasoning principle for this, right? So notice that that's actually pretty similar to what the actual behavior of x gets v is. When you do a store into x, we move from a state where x has some arbitrary value to one where x has the value we're storing, right? It does an update in place to one cell in the memory. Something very similar is going to happen in this proof. We find x points to 0 in the precondition, and we replace it with x points to y. Sorry, I didn't mean to highlight this. So the way I think about this is the proof itself is like an imperative update. What we're doing is we're updating the precondition and mutating it to replace this x points to 0 with x points to y. And then the frame rule is simply the fact that when we do in-place updates, nothing else changes. This gets carried through without being modified. That's what the frame rule tells you. It tells you that it's okay to do updates in place. Nothing else that you have is going to get modified. The reason why the frame rule is true is because the separating conjunction guarantees that these are disjoint pieces of memory. If they could overlap, then this would cease to be true. Modifying x could easily modify what y points to as well. And then just to complete the story, the next thing we do updates a different part of the assertion that we have, and updates y so that it points to x. So are there any questions about this intuition? I think this is probably one of the biggest things I want to get across is separation logic is about making these in-place updates to the assertions that you have available. And these assertions are kind of like a symbolic heap. So these assertions are pretty similar to the memory, except that they're logical. They're not, these aren't literally the contents of memory. They're instead just a description of memory.
I have a question. So if in this second part where you have x points to y and separately y points to 0, are these two separate like y's? How can we have this star in between them if they're the same y?
Yeah, that's a great question. So this is, this easily gets confusing in these pictures because we have to distinguish between the literal value of a pointer and what its contents are, right? So what's going on is that we have some memory, right? It has some address x. So what x points to y is literally this picture for RAM, right? It says that the RAM has some x, which is an address, right? That's a location in memory. And what we've stored inside x is y. So the footprint of x points to y, the memory cells that it covers, is just x. The y here is immaterial. It's just what we happen to be storing in x. And y just happens to be a pointer valued variable. Does that make sense?
The value of y or the address that
So
y is at is being
y
stored?
is an address.
Okay.
Right? When we say, okay, so maybe it would actually help to like do make this imaginary and concrete. So here is like an example of how this might be true. Right? I picked random small numbers. So now we can make this concrete. So I chose a higher number for x. So x maybe goes here. The contents of the memory at 0x3 are hex 37. And the contents at address 0x37 are 0xf3. This is what it means to have these two things in a cycle. Does that make sense?
Yes. Thanks.
Cool. Yeah, things get really confusing once you start replacing everything by variables and variables that happen to have pointers. Okay, so I want to take this as an opportunity to go back to the delete tree example and explain why this is cool. So I'm just going to draw out this kind of in-place reasoning for delete tree, and then I want to highlight some interesting things about this. So, oh, sorry, I'm going to use this definition of delete tree. This is just the memory safety part. I'm going to skip all of the binary search tree or like values in the tree business because they're not really important to this example. So let me just write out roughly what the paper says, but in my notation, so it's consistent. So recall that a tree is either points to none if it's an empty tree, or it has two child pointers, and those are themselves trees, the roots of trees. So let's do a proof of delete tree. In the special case, and I'm going to do this proof only for the case where there's something interesting going on. So there's actually, T turns out to actually have some child pointers. The other case is really easy. So, sorry, I'm running out of space. Let me move this. The first thing that we do in this case, so the implementation for delete tree, which is spelled, I misspelled it, okay, delete tree, is it deletes the left child, right? So delete tree is gonna recursively delete the left subtree, the right subtree, and then the root pointer to free up all the memory. So what happens when we delete the L? Well, as I said, we find the precondition to delete tree. Oh, let me remind you what the specification for delete tree is. The overall specification we're proving is that if we have a tree at T, then deleting T results in emp. This is just a memory safety proof. All it says is delete tree is not going to try to free things that are already free, and it's not going to touch any memory outside of this tree. That's what that's what this specification in SL means. Okay, so the first step of this proof was we recursively apply delete tree. I'm just going to drop the emp. So remember that emp just means there's no memory. So p star emp is exactly the same thing as p. So I'm just going to collapse the emps and get rid of them. And then the rest of delete tree is pretty straightforward. As you can imagine, it does the same thing on the right child, getting rid of that. And then finally, we free the root pointer itself. And we're done. So we operated on this, on the left tree, the right tree, and then the root pointer. And then we're all done. Okay, so this proof, when you first see it, it might seem like, yeah, that's completely obvious. Of course, that's how it works. So just to highlight why this is interesting, let's try to imagine how we do this proof without separation logic. Okay, so how is that going to work? First of all, let me rewrite the specification because we no longer have this tree predicate. We have to say something else. I'm going to write my specs with this H for the heap. So now these preconditions have to explicitly talk about the heap. This is a little bit like in the labs, how we have a sigma, right? We talk about this sigma state. In this case, the state is the contents of memory. This is a pretty low-level state. So what we're going to do is we're going to say that if there is a tree in the heap, then after running delete tree on this tree, we need to specify what the new heap is. Okay, so before we just said emp, so let's try to get away with just saying nothing here. So we don't really care what the new heap is. We just want to prove that delete tree is safe. Okay, so that's fine, but how are we going to, now imagine what we have to do to prove that delete tree of L. So now we're going to have to do a proof that starts with tree of T comma H and deletes the left subtree. Okay, so, and I'm going to use this opportunity to, I'm going to write down what tree of T comma H actually says. Since again, we don't have separation logic, so we need to say this manually. Okay, the first part's going to be pretty similar. The heap at T, right? T, we want to say that the memory contents at T is L comma LR, the two child pointers. Then we need there to be recursively a tree at L, and we need there to recursively be a tree at R. So let's just say those things. That's fine. And maybe we should probably say that T, L, and R are distinct just to avoid overlapping memory. That seems good. So let's just say that. Okay. So now what happens if we run delete tree of T of L? So we need to delete the left tree, and then we're going to delete the right tree later. What do we know of the resulting heap? Well, our spec actually says nothing. Here, it just says true. That's pretty bad. That means we're not going to be able to run delete tree of R after this. We can't prove that it's safe to delete the right subtree. Okay, so the problem is really that the specification is far too weak. We should probably strengthen it. And instead of this true business, let's say something more precise that says, well, we're not going to modify anything outside of the tree. Okay, so we're going to say for all pointers, h prime of that pointer is the same as the old value if p is not in the tree. So I'm going to say unreachable from t. Okay, so how do we make use of this specification on the right-hand side in actually doing this non-separation logic proof? What we need to know is that when we delete this left thing, all the other stuff is preserved. We need to know that there's still a tree in the right subtree, that in particular, this thing is unaffected. How do we know that the right subtree is disjoint from the left subtree? Well, we actually don't. We should probably add that to the tree predicate itself. This thing should probably say that instead of just saying that T, L, and R are distinct. Okay, so I'm not going to finish this proof because this is already getting to be a huge pain, right? So you can kind of see how we're reconstructing all of the tools of separation logic. We needed to apply we needed some sort of frame rule-like thing to show that even after running delete tree of L, tree of R in this new heap is still true. We needed to specify that the memory addresses touched by the left in subtree are disjoint, not just this fact, right? This is insufficient to do this proof. And we needed the specification for delete tree to promise that only tree is modified, only the tree is getting touched, nothing outside. So does that make sense? Can you kind of, is it clear what separation logic is buying us to prove this example correct? Okay.
I guess.
Eileen,
sorry.
you have a question. Yeah, go ahead.
Yeah. I'm not sure if you were kind of asking that as a question, but it seems like it's just something of a shorthand, something of like an abstraction away from all the nitty gritty details of like how you would write it out in Hoare logic, but it just makes it easier to reason about all of this.
Yeah.
That's my interpretation.
So one view of separation logic is definitely that, well, it's a really concise shorthand for all the stuff that you're inevitably going to have to say if you're doing proofs about pointers. I think that this separation logic proof is so much nicer than the Hoare logic proof that it becomes quite a different beast, right? So we really couldn't carry, like, this is a really simple example, right? We're talking about memory safety of just disposing of a tree. Doing a proof about a binary search tree is probably considerably more complex than that. or a more sophisticated data structure. So I think separation logic is qualitatively different from just the trying to do it in OR logic. But indeed, like if you just look on the surface, it certainly seems like all we've really done is we've come up with a very concise shorthand for this kind of memory safety stuff. I think separation logic is certainly good for this kind of memory safety proofs and for sequential programs. Where it really shines is probably concurrency, in my opinion. And I think in Horan's opinion, it's probably in automated reasoning. I think both are true. But these small examples kind of help you get a handle on what is going on in separation logic and what do these predicates mean? What does this star thing mean? And separately, I should say. Okay, so I have just one more part to this lecture, which is I wanted to do something kind of fun, which is to show you an example of separation logic in Caulk. Okay, so we need a little, and the example I'm going to use is this Deletery example. So I'm going to show you a mechanized proof in Caulk of the Deletery example, which will be machine checked. I'm not going to use the lab infrastructure because the lab infrastructure doesn't have separation logic. I'm instead going to use something called Iris. So we'll later see Iris in the context of concurrency, but the nice thing about Iris is that I can show you Iris without using any of the concurrency features and just using the vanilla separation logic stuff. So there's one thing that I need to prepare, that I'll prepare for you before I actually show you the Caulk stuff, which is how to understand the goals that we're going to see in this proof. So what does a Caulk goal look like? So when you look at the proof window, it looks something like this. Caulk shows you various hypotheses. It draws a line here, and then you have some goal. Okay, so these are some hypotheses, and this is some conclusion that you're trying to prove. And when you interact with Caulk, you apply various tactics, and the state gets updated. You know, your hypotheses get modified, your conclusion becomes simpler, hopefully, over time, that kind of thing. So what in Iris is kind of a has a domain-specific language for doing separation logic proofs. The domain-specific language looks a lot like Caulk itself. So it also has some hypotheses, which are Caulk hypotheses. So there's still a Caulk context. So we call this thing a context. This is all your Caulk hypotheses. Then below that Caulk line, the Iris DSL is going to show you separation logic preconditions. Okay, so notice that the things I'm now writing as hypotheses, they are no longer Caulk facts. These are separation logic assertions, and it's actually going to use Unicode, so it looks like this. Then it's going to draw another line for you with a little star at the end, and then some goal. And this is also going to be a separation logic assertion. So this thing is something we call the spatial context. Spatial because of this intuition that it's in separation logic. These things talk about space. They talk about the heap. And then there's also an actual goal. So this is the goal or conclusion that we had from before. Okay, so what is the upshot of this? What you get in Iris is a bunch of tactics to help you manipulate these spatial hypotheses as if they were in the same way that you manipulate Caulk level hypotheses. And the meaning of a proof in Iris is when we see this goal, what we're actually proving is that the separating conjunction, the and separately of all of the spatial hypotheses, right? So this is I took the star over all the things in the spatial context and I got rid of the names. So of course the names are just to help you talk about these hypotheses. They don't have any other meaning. And what we're going to be proving is that all of these hypotheses imply the conclusion. Okay, and I've chosen this example so it's actually a true statement. It is true that these hypotheses imply this conclusion. You just reorder them. So that's something that we need to just be able to decode what the goals will look like. And then there's one more thing, which unfortunately I can't get rid of, so it will show up in these proofs, which is Iris doesn't use Hoare triples. They instead use this thing called a weakest precondition. It's sufficient for you to remember that when we say P implies the weakest WPE of Q, then it's the same thing as this Hoare triple, right? So the meaning of this WP is if this holds in a heap, then running E in that heap will produce a state satisfying Q, okay? So remember that that's what this Hoare triple means. If we start in a state satisfying P and we run E for a little bit to a new state, then Q of sigma prime holds. WPE of Q is just is like this, but it's a property of a state that says when WPE of Q holds in some state, then the rest of this figure, this stuff, is true. If that was confusing, again, just remember that this is, just translate to Hoare triples in this way. Whatever we're assuming implies this Hoare triple. Okay, so I'm going to switch over to Caulk and just go over this Deletery example briefly, but using Caulk instead of paper. Okay, so I will skip over this part for the most part. So this is the, hold on, is this big enough? Let me make, let's try to get this bigger. Okay, so I had to implement Deletery in order to prove it correct. Hold on one second, I think my screen sharing is not working. Okay, so I had to implement Deletery. There's a bunch of comments, but basically it's following the same structure that I was using for all the tree predicates in this lecture. X, which is the root pointer, is always going to be a pointer. We dereference it, and either it's some tree and it has some children. If it has children, we delete those subtrees and we free the root pointer. And if it points to none, if there's no tree there, then we just free the root pointer and we're done. Okay, so I'm going to skip ahead. This is the definition of tree, more or less. So what it says is tree is either T points to none, or there exists some subtrees, T points to those subtrees, and there are subtrees, those are themselves subtrees. Ignore this little diamond thing, which is pronounced later. It's not important. Okay, so as I said, we're going to prove Deletery correct, and the way we're going to encode that is the precondition implies this WP. The specification only implies memory safety because we're not saying anything about the resulting heap, but we could do more sophisticated things in separation logic. So, you can sort of ignore the actual tactics that I'm executing, these things starting with I, and just focus on the right-hand side, the proof goal that we're observing. So, as I said, this is the Caulk context. This is what you're used to. And then this is the new fancy thing that Iris is giving us. It's giving us a spatial context with assumptions like tree of T. This is another assumption which says, if you look at this, you'll notice that it says that Deletery follows its specification. It says Deletery goes from tree to app. That's how we do recursive proofs in Iris. You're allowed to assume that any recursive subcalls satisfy the overall specification you're trying to prove. So this comment gives some details on why can't we just why can't we just apply this hypothesis right now and finish our proof? And iris prevents you from doing that. So like, suffice it to say that you can only use your specification on actual subcalls. You can't just use it to trivially do your proof. So what we do is what this destruct tactic does is it does a case split. So remember that tree is an or. It's either none or it's some. So we do our proof, we break our proof into those two cases. In the first case, this is the none case, we're going to dereference the tree and we're going to find that it's empty. And so the remainder of the proof is just a proof about freeing the root pointer. This is the easy case. I pretty much skipped this in the lecture. The other case is the more interesting one. So this is what I showed you on the board, right? So this is what happens in the second subproof. We know that T has some children pointers, and we know those are trees, and we have this assumption that Deletery follows its specification for the subcalls. I've done this a little bit explicitly, but what I'm going to do here is I'm just going to appeal to this intuition that when we apply the Deletery specification recursively, okay, sorry, I'm going to skip ahead to, let me just replace this proof with something simpler. Oh, never mind, that's not going to work. This is why you don't live code. So what we're going to do is we're going to apply Deletery, the specification for Deletery recursively on just the tree of L hypothesis. So we do that, and you can see here that we've disposed of it and replaced it with emp. Then, and that covers the first instruction in the first line of code in this implementation. Then we handle the right subtree similarly. So we use HR, this thing, tree of R, to prove that the right subtree can be deleted safely. That again uses the induction hypothesis. We recursively use the specification for Deletery. And the result is that second or that third state where we just have a root pointer and we've gotten rid of all the subtrees. Then the rest of the proof is pretty simple. We're just going to free the root pointer and we're done. So remember, like, the upshot of all of this was we proved that Deletery is memory safe. And we did it even though Deletery has to be applied recursively to the subtrees. Are there any questions about that while I still have Caulk open? Okay, then I'm happy to take any overall questions. Otherwise, that was all I had to say about separation logic.
Could you just go over this like WP notation again?
Oh, sure, yeah. So let me switch to sharing again, one sec. Okay, so the thing that you have seen is Hoare logic, where the meaning of this expression, so this is a prop, right? This is an assertion. This is an assertion that we state that says E follows the specification. E is some program. What this thing means is if we start E in a state satisfying P, if we do all of these things, then the specification says the final state is going to satisfy Q. And I'm ignoring return values for now. There's an alternate way to represent specifications of programs, which is this definition WP of E for some postcondition, which is the weakest precondition, which is what's called the weakest precondition. The weakest precondition is from state to prop, and the definition of this thing is WP E of Q, the weakest precondition of E for Q, is true in some state when the rest of this thing holds. So when running E from that state implies that the postcondition holds. And the reason why you use this is probably mostly technical for the sake of this class. But the nice thing is that by having the state to prop, this is something that's actually in separation logic. So we can talk about things like P entails WPE of Q. So for example, we can say X points to V0 entails the weakest precondition of, say, loading. So I don't remember the notation the paper used, but load X is the same thing as bang X that I had in my code, or in C, dereferencing X. We can say that the effect of loading X is we return the current value, and the postcondition includes X still points to V0. So the nice thing about using WPs is that everything lives within separation logic. I only have separation logic assertions here. This is in separation logic, and the overall weakest precondition is also a separation logic assertion.
Right, that makes sense. Thank you.
You can think of weakest preconditions as like a very important implementer's trick. If you're implementing a separation logic, this is probably or a system for doing proofs in separation logic, this is probably how you want to do it, rather than actually using core triples. Okay, if there are no more questions, then we can end a couple minutes early.